Morning or good afternoon, depending on where you're joining from. Just a note to let you know we're going to give it 1 more minute for people to come into the room, and then we will begin. Thank you. All right, so good morning, good afternoon, and welcome to the concentrated solar heat for commercial industrial industrial applications in Asia-Pacific. This is an online session that aims to teach you a little bit more about this wonderful technology and its uses. And here with me today, I have two key experts on the topic. I have Safir Wahid. Hi, Safir, where are you joining us from? Remember to mute your microphone. Unmute your microphone for me.
Hi.
So where are you joining us from?
I am Safir from Lahore, Pakistan.
Excellent. So Safir is in Lahore. And Sid Malek or Sidharth Malek, where are you joining us from?
Hi, Belen. Joining from New Delhi, India. Great
Excellent.
to be here.
Thank you very much, guys. And I'm in Madrid, and I'm looking forward to hear where you guys are joining from. Please do share through the chat. We usually have a lot of countries represented, so it's good to see that these sessions are so international. And before we start, I'd like to ask you guys a few questions. It's going to be really quick. All you have to do is just literally, I'm going to throw a poll in your screen. And what I would appreciate is if you all answer. They're very simple questions, okay? Let me just throw the first one in. So I think you can see that on your screen. It's very simple. Are you considering a CSH solution for your business today? I just want to know if somehow, somewhat, you've considered the technology. Maybe you want to become a technologist for this. Maybe you want to consider it for something that you or your clients need. So we just, wanted to get an idea of who's there in the audience and what are they thinking in terms of this technology? Is it something they're considering today, or perhaps for the future? I'm going to give you a few more seconds. Please, let's get in those last few votes. Right, 3, 2, 1. Let's see what people say. Right, you guys can see that? So you can see that 63%, although I have to say that not a lot of people have voted, but 63% say yes. And no is the extra 38%. Perhaps we will do best if I ask another question. And this is going to be what I'm going to be asking. How are you interested in this technology? So what are you hoping to do with this technology? Are you a researcher? Are you hoping to use it, this knowledge and this technology in terms of researching it? Are you an industrialist? Do you want to use it for your own heat and steam? Are you an ESCO that want to offer this service to your clients? Are you an end user? Are you a regulator? I would just like to hear, what are you thinking in terms of this technology so that we can make an idea. So let's give you a little bit. We know that the questions are a little bit strange. They might not be all applicable, but just as in large, so that you can understand. So far, what I can see is we have researchers, we have ESCOs, we have some end users. We don't have a lot of industrialists here, unfortunately. But let's just get the few votes in, the last few votes. So 3, 2, 1. Let me just show this. So as you can see, most people are researchers. There is some ESCOs here. Actually, most people are ESCOs, some researchers, and others. So we now know who's in the room. I think you can't see that anymore now. And let's go then. Sid, you're going to be the first one up. So if you could please share your screen and give us your speech. And then we will take it from there. Next one will be Safir. So go for it, Sid. And in the meanwhile, I'd like to welcome people from Denmark, from Germany, and just to let you know, we are recording this online session, and we will have the PDFs available for you. So worry not, all the information will go to you. And Sid, go ahead.
Great. Thanks, Belen. It's great to be here, and I welcome all as well. I think over the next 10, 12 minutes, what we're going to be doing is talking about what we do in this very, very interesting industry, concentrated solar heating. My name is Siddharth Malik, and I lead Megawatt Solutions, which is a New Delhi, India-based technology and solutions company. Just a little bit about what Megawatt Solutions is all about. We're a core technology and solutions company for clean and emissions-free heat. That's how we like to position ourselves. There are a couple of things that we do not do, and that is solar PV power stuff. But we are experts when it comes to heat and heat-based indirect and direct applications, such as cooling, evaporation, drying, et cetera, et cetera. Typically, we work with commercial and industrial manufacturing companies. That could include a lot of manufacturing plants and industries that have a tremendous requirement of heat. Ironically, the number actually sometimes is even more than power for certain industries such as bitumen and whatnot, where the heat load actually is far more than the power load of the industry. We understand it's a technology, but it ultimately has to translate into a solution for the end customer. So we're a turnkey technology and a solution provider. What that implies is we have our own design engineering teams. We have our own manufacturing of everything that we provide. Of course, we undertake installation, erection, commissioning, and we also take long-term operating and maintenance contracts so that the customer ends up dealing with one-stop shop, kind of one technology and one solutions team. We're based out of India and have traditionally focused on India as a market. So we have across India, we have very large project and service teams. We, of course, are also doing projects overseas now towards Southeast Asia, in China, and just looking at some parts of Middle East and the US as well. In this niche industry today, we're one of the leaders in the Indian subcontinent with more than 30 to 40,000 square meters of cumulative installation area of concentrators. And we have our own manufacturing capacity, which is geared up for very large demands that we see coming in this space globally. So we can actually manufacture up to 100 megawatt thermal per year out of our own manufacturing facilities. Over the past 6 to 7 years of our journey, having started this company and taking it to where it is today, we have been awarded globally as well as domestically by a lot of government, semi-government, as well as the private sector in doing continuous technology innovation in concentrated solar thermal. And some of the photographs are just there for your reference. So let's get into it. The solution that we provide is called the Megawatt Solutions MWS Solar Field. And solar field, we believe, is going to redefine how industries actually generate and utilize heat today. We started looking at concentrators, and they've been around for a very long time, such as parabolic troughs and Fresnels and power towers. We wanted to do something which was more suitable for the industrial space, where land is a constraint and other things. Of course, we don't have all the conveniences as one would have in a utility scale power plant. So we looked at how conventional boilers work, radiative heat transfers. We looked at the power of concentration, which I'm sure most of us have been around there as kids or even as adults. Then we, of course, look at the sunflower, which in a very, very small footprint maximizes its energy generation simply by tracking the sun. Inspired by three very, so to speak, unrelated phenomena, we came up with a technology which is called the Paraboloid Dish, which leverages some phenomenal features from all these three applications: heat transfer, concentration, and tracking the sun. And this is what it looks like. What you see on your screens is a Paraboloid Dish concentrator, which is, it resembles your TV satellite dishes to one extent. However, it operates in the optical frequency range. So it actually takes in the incoming thermal part of the sun's radiation, which is direct normal insolation, abbreviated as DNI. And this parabolic shape in 3 dimensions actually concentrates that incoming radiation onto a central focal receiver point. There's a receiver at the top, which you see is a very, very bright spot. That brightness just emanates from all the cumulative radiation that actually add up at the focal point of the dish. And the stagnant temperatures, which is the instantaneous temperature in the beam, can actually be easily 1200 to 1400 degrees Celsius. What that does is it allows you to heat any working fluid, be it water, steam, oil, air, etc., and bring it down from the top of the dish to be taken to an end industry for any application. There are a couple of very interesting things about the dish. Top to bottom, it's a very large dish. It's about 11.5 meters in diameter with a total aperture area of about 100 square meters. But its ground footprint, that is the area that the dish takes on the ground, is less than 1 square meter. So it has a 1 meter by 1 meter footprint. And the entire dish can stand as high as 6 to 7 meters above the ground, thereby freeing up the installation space, which typically is very, very starved in industries. The system achieves very, very high efficiencies owing to the fact that it has very high concentration ratio. What that implies is how much energy have been able to take from what kind of incident area and how tightly one has been able to kind of concentrate it onto a focal point. The concentration ratio exceeds 700 to 800:1, which implies we have been able to concentrate the incoming energy 800 times, which of course results in very, very high temperatures, and above all, extremely high efficiencies, more than 80%. Now that is thermal conversion efficiencies of 80%, and compared that to something like PV today, that is less than 20%, at least in the commercial scale. These are fully automated systems. So the system actually tracks the sun in 2 axes, both north, south, and east, west. And the reason we do that is in order to maximize the incoming radiation so that it can result in maximum output and much better returns for customers' investments. This is a modular system, which is rated at about 3 lakh kilocalories per day. And these are added in series of parallel combinations, as shown in the picture, to actually arrive at the total heat quantity that is required in industries. The solar field consists of 3 parts. One is the solar dish concentrators that I just talked about. We also undertake process integration and automation. We recognize it is just not about the thermal energy source. It's also about how well is it getting integrated into the end process, which could be a boiler, a heater, an end application in industry. And we design the complete instrumentation and piping network, at what temperatures, what pressures the heat actually needs to get transferred from one point to the other. And we package all of that on a turnkey basis to deliver heat, which can be ultimately used for a variety of applications in industries, for process heating, for air conditioning, cooling, power generation as well, and other ancillary applications, such as water desalination, wastewater evaporation, and so on and so forth. So the solar field is an integrated approach towards displacing fossil fuels, all packaged into one solution for process industries. We often get a concern from industry users that, great, I have a boiler, I have a heater, and you have a great technology, but then how do we ensure that the 2 systems are married together the right way? So we recognize the value of integration being an extremely and a crucial point for any industry. So we have both direct integration as well as indirect integration methodology. In the direct integration, we actually directly integrate the solar field, which is collection of dish concentrators, directly into the customer circuit at the appropriate location in the boiler circuit. So the 2 systems are thermally as well as mechanically coupled. In an indirect integration approach, which is more common in pharmaceutical and food industries, which are very, very sensitive, we adopt a heat exchanger by which the solar energy and the energy to be integrated are thermally coupled, but mechanically decoupled. So any effect in one system never translates onto the other, and vice versa. Ultimately, by both, we ensure there is no impact on the customer end process, which is of course extremely crucial for any manufacturing industry, as the solar field actually gets integrated at the back end or the utility end. Based on this simple concept, we've done work across different industry types: pharmaceutical, textile, chemical, paper, pulp, food, etc. across a different variety of working fluids ranging from hot water, pressurized hot water, steam, thermic oils, and hot air across a different temperature range. And as I said, the critical point here is the solar gets fully automated, integrated with the existing boiler circuit. So nobody actually has to worry about when my solar is available and when it is not. Any shortfall in energy is automatically made up by the fossil fuel boiler that already exists in the industry. So make hay while the sun shines. That is the simplest approach that is used here. Why parabolic dishes? It's a question that comes often to us. And we believe that paraboloid dishes are very, very unique in terms that they have no cosine losses, which are typically observed by parabolic reflectors. Typical parabolic troughs, which are very common, utilize a north-south axis and a very long length of land piece required, which is not always available in industries. And that's part of the reason parabolic dishes actually do not have that requirement. They can be planted anywhere. And since they are two-axis tracking, they'll actually locate the sun, and direction is not a constraint. Of course, the footprint of the dish versus the footprint on land, as I said, is an order of 1:100. And this is just a small example to tell you, this is an example with one of our customers where there is no contiguous area of land. But since we're using parabolic dishes, these can be interspersed and spread out as and where the land parcels are available, unlike a trough or any other system. Last but not the least, paraboloid dishes have a phenomenal efficiency compared to most other technologies at least available today, owing to their high concentration ratio, much higher conversion efficiencies, and other interesting things that I'm sure my colleague will also talk about. That was a very large ground mount system, M100, which is 100 square meter of concentrated area. Of course, we recognize the need for industries to have rooftop installations like solar photovoltaics. That's the reason we have a model M20, which is a 20 square meter paraboloid dish, which can be easily installed on a rooftop. And these can be done once again in series and parallel combinations based on the quantity required. Of course, all the features of a large dish, which is two-axis tracking, automation, very high safety and high temperature capabilities, are all the features that are part of the smaller other dish models as well. So here's a photograph where a group of M20 paraboloid dishes are actually installed on a RCC rooftops. And it's creating a whole different paradigm compared to conventional flat plate collectors and even other technologies that have struggled to actually give maximum energy out of a small given area. Just a quick run through on where these things can actually be used. So if you start on the top left, that's a collection of paraboloid solar dishes which provide steam and pressurized hot water in pharmaceutical and the dairy sector. On the right, you have a hot air generation application where we generate hot air up to 250 degrees Celsius. And that air is then subsequently used in the food, the textile industry, and for sludge drying kind of applications, where hot air is desired, since you don't want to touch the sludge. And sludge could actually have all sorts of chemicals. So this makes a very, very strong value proposition for the customer. At the bottom left, you see a paraboloid solar field, which is used by the rubber and the polymer and the chemical industry. Range temperatures from 200 to 300 degrees Celsius. And last but not the least, a typical application of pressurized hot water, which is commonly used up to 200 degrees Celsius in various different industries. The point is, paraboloid dishes are very, very flexible to be able to operate across a very wide temperature range. And they're modular systems, so they can be actually packed into a solar field as and when required. So the next couple of slides, I'm just going to give you a quick snapshot of these. This is very real. It's not R&D. It's out of the lab. These are commercial projects. They're very large-scale projects. So here's a project that's been running for almost 4 years for India's largest dairy, which is the brand name Mother Dairy, where we're displacing natural gas by a solar field, which provides up to 40 lakh kilocalories per day, right? Here's another one, which is one of the flagship projects in the country for National Thermal Power Corporation, which is one of the largest, excuse me, largest thermal power utility in the country, as they set out to look for interesting solutions for their own coal displacement in their existing thermal power plants. They looked at Paraboloid Dish technology as a very interesting choice. So here's a photograph of a project which we have done right next to the cooling towers. The size of the project is not very large, but what it has been able to do is create a confidence in the thermal power, or what I call the conventionally brown industry, to actually adopt green energy into their existing brown facilities. And these are projects which have been operating for more than 3 to 4 years, consistently delivering heat, and most of them have paid back their investment by now. A pressurized hot water application for a pharmaceutical industry where we're displacing natural gas. The project is also in a different part of the country, which has very, very high hurricane and wind zones. So the system is designed for 200 kilometers per hour of wind gusts at the bottom of the foundation. We recognize it's a large system, and all the safeties for wind are all inbuilt into the system, whereby when the wind comes, the dish actually go into what is called a noon or a safety position, and then revert back fully automated based on when safe operating conditions resume. So this is a project which is actually in a hurricane wind zone area in the country. And we are proud to see that this project has already seen 4 hurricanes and it's been operating absolutely just dandy. Yet another very interesting project and a very unique application for concentrated solar thermal, where the heat is used for sludge drying. Industrial sludge generation is a very, very problematic area globally. And it's a problem that actually cuts across different sectors, different geographies, and different sizes of industries. A small industry generates a small amount of sludge. A large industry generates tremendous amount of sludge. We use concentrated solar thermal heat to enhance the evaporation rate of the sludge so that it can be dried from a conventional 20, 30, 40-day cycle to a matter of days, single-digit days. What that does, it allows the customer to have a drying solution which evaporates the water out of the sludge at absolutely zero cost using green energy. So green energy being used to treat a very, very dirty and a brown problem. And that too at almost no capital cost. What I mean by that is we install these systems and we have an ESCO model approach whereby we actually install the system and we charge on a per ton basis to the end customer. So the customer does not have to incur any upfront capital cost, and he or she gets sludge drying consistently by solar thermal, clean, zero emissions at a fraction of the cost. So it addresses a huge environmental problem that persists across the world today, and we are proud to actually share this with everyone. Mondelez, a brand that is globally known. Of course, we know them as the Kit Kat and probably, sorry, not the Kit Kat, that's Nestle, but the Cadbury's dairy milk, right, in this part of the world. And we are happy to contribute solar energy into manufacturing of that chocolate for the world. So we're doing a very interesting project for Mondelez in one of their India plants, where the energy, the steam is actually used for the CIP and the pasteurization process in the industry. Last but not the least, a very interesting technology and a solution that we're bringing to the wastewater industry, where solar thermal and other energy sources, could be LPG, diesel, biomass, whatever is available, are actually hybridized. And that energy of the two sources is actually used in various different forms. Could be tunnels, could be insulated vacuum vessels for a variety of drying applications. And I want to just quickly give you a short example of how this is done. A solar field consists of various dishes is actually all installed, and it generates hot air up to 220 degrees Celsius. And this hot air is actually channeled onto an existing sludge drying bed or a wastewater drying bed. What you see on the part of the image are wastewater ponds or sludge drying ponds, which are open to atmosphere, and they rely on atmospheric conditions for evaporation. Of course, so that drying happens in ambient air conditions, right? 30, 35, 40 degrees Celsius. What paraboloid dishes are able to do is enhance that drying and reduce the moisture content of the product. That could be a paint, that could be a sludge, that could be wastewater, very, very quickly. And this is how it looks like. In this particular project, we worked with a sludge drying company, which actually manufactures these very large tunnels, and we push in hot air, thereby making it like a multi-effect evaporator, but powered by concentrated solar thermal. The very, very hot, dry air enters from one side of the tunnel, picks up the moisture from the sludge and wastewater, and the moist air is actually vented out at 95% humidity, taking all the moisture away. What gets remained behind is actually quite phenomenal. This is what the system looks like. This is also installed in a very, very high wind and an earthquake zone in India. And we're proud to say that these large dishes have survived years of earthquakes and hurricanes. We start out by feeding a sludge slurry into these drying tunnels, which have more than 60% moisture. And by the time the drying by concentrated solar thermal is done within a period of 6 to 10 hours, what comes out is extremely dried pigment, which has a moisture content of less than 1% or 2%, thereby actually almost making it look like a powder. This simple process can be extended to any drying application prevalent in the entire world today. Pigments, etc., etc. So with that, I think I just want to conclude by just talking about ultimately how it all stacks up commercially. We've looked at various different industries, the kind of fuels that they use, dairy, petroleum, pharmaceuticals, food processing, and they all have different kind of costs of energy today. This is $ per megawatt hour thermal. And glad to report that Megawatt Solutions Paraboloid Dish actually has a levelized cost of energy, which far surpasses the economic value of any other kind of fossil fuel today. This simple idea creates a very strong value proposition. And I think at that note, I'm just going to sign off and thank you for all your attention. And over to you, Belen.
Thank you very much, Sid. I have to say, I have really enjoyed seeing the pictures and hearing about the amount of things that you guys are doing. It's so diversified. It's really, truly amazing. So really, really interesting. Thank you so much. And Safir, this is your turn. If you could please share your screen. And then I know I can see that there's been a few questions. Safir's been doing a good job, answering those, but we will probably bring them back live so that we can all learn. Safir, whenever you're ready, please share the screen.
Sure.
And just to remind you, we are recording this session. We do have the PDFs, which we will put in the landing page for you. And you can ask questions, as we said before. Please send them. We will have some time to answer them. And here we are. Safir is ready. Let's go for it.
Hi, I'm Zafar. I'm the founder and CEO of Z Solar. We also, are in CSP and CSH solutions using the Parabolic Dish, similar to Siddharth's technology in some ways. Sorry. Yeah. Okay. There we go. So, the dish is the perfect concentrator shape. It's very flexible due to very high concentration ratios, as mentioned previously. And this great flexibility means it can be used for many, many applications, industrial process steam, solar thermal enhanced oil recovery, desalination, and also power generation with thermal storage. The flexibility of the dishes is not just in the output conditions, the heat and the steam conditions they can generate, but also in the land utilization, in project flexibility and robustness. So it is really a very good type of solar concentrator. So, we call the dish as CSP 2.0, and, why do we call it CSP 2.0? Well, firstly, they have an ultra-high net solar to thermal conversion efficiency of 88%, and that is the net energy from the sun coming in to what is going out in the form of heat at the exit of the solar park. I know this figure sounds quite high, but in the following slides, I will also explain how we get to this figure. So dishes can be very robust. We have shown and proven this as well. They can withstand desert environments, they can withstand dust storms, they can withstand all sorts of different varying conditions. Another big advantage with dishes is that since each dish has this high concentration ratios, it can achieve the right steam conditions, meaning that it's a fully modular and decentralized system, which means if one dish were to go down in a park of 100 dishes, then you still have the rest 99 operating. So it's a very robust system in compared to, say, for example, a tower where you only have one tower, and if it fails, the whole park stops. Furthermore, what we have done is we have also built an automatic cleaning system. CSP systems need the mirrors to remain clean so that they can effectively focus the heat into the receiver. And cleaning these is a cost, so we do it automatically. Dishes also can be moved around, so ours is a semi-mobile design, which means that if the system has a 25-year life and it's to be installed at a site which maybe will only be operational for 5 or 10 years, it's possible to move the system onto a different site after that time period. So moving back to the first thing, how do we achieve 88% net solar to steam conversion efficiency? Well, if we look at the diagram at the bottom, we see that 100% solar energy which comes in, 95.1% gets reflected back into from the mirrors. This is the reflective efficiency of the mirrors. Of this 95.1% which gets reflected back, 99.3% enters the receiver, and then the thermal receiver has a conversion efficiency of 92.4%. And if you add all of these up, that's how you get to the 88%. And this is not theoretical, it's well proven in many technical papers and in many different installations as well. Overall, the system is very robust. As you see, it's the energy absorber is basically a boiler, which has no moving parts in it, and is also able to do this very effectively. Now, the efficiency that dishes have is something it's maintained throughout the temperature curve. So if we look at the top curve, we can see that at 100 degrees Celsius, the system is around 90% efficient. And then as we move along, it drops to about 85% efficiency. And the 88% that we measure is at about 320 degrees Celsius, which is a kind of middle of the temperature range. This beautiful flat curve also means that the system has an operational curve which is nice and flat as well. So if we look at the bottom right curve, and these are real performance data, we can see that the system in the morning ramps up very quickly, and for most of the day it's actually producing at above 80% of its capacity, which means that the energy that's coming out is usable. It can easily be integrated into an existing hybrid system. So for example, if you have an existing boiler, it can be easily powered down and stay like that for throughout the day. And then at the end of the day, it can be powered up again as the sun goes away. So really, again, coming back to this 2.0 versus legacy CSP solutions such as Fresnel or parabolic troughs, we see that there's a very high optical efficiency with dishes. If you can see the dish thermal on the graph on the left has this high optical efficiency, a fairly good receiver thermal efficiency as well, and also a decent piping thermal efficiency. And when we combine all of this, we really come to see why dishes can give this overall 88% annual average efficiency. Unlike, say, parabolic troughs, which are, in best case 50 or typically even below 50 when you look at the annual average due to cosine losses as the sun latitude changes, throughout the year. So some of the questions were asked about land utilization. So trying to put that into perspective, we can see that one dish on the bottom, that one dish generates the same steam as the equivalent parabolic trough and the linear Fresnel. So for industrial applications, this is very important because, you know, land is obviously a scarce commodity. So not only is the dish flexible in the sort of in the arrangement, because we don't need long or rectangular or fixed level ground. It can be variable, but also we're typically using a lot less land. So if we look at the land requirement in the bottom left-hand figure, sorry, one second. Yeah, if we look at the land requirement, you know, a dish needs about 215,000 square meters for 500 tons of steam per day, versus, you know, a significantly higher amounts for parabolic trough. And then also because the dish is very efficient, the mirror area is significantly less in compared to other technologies. So this has the effect of obviously helping to reduce the capex, but also the operating costs in terms of water consumption used to keep the system clean. So, I mean, the dishes are an important part of the overall technology, but they are not the only part of the solution. It is the complete solution that we provide as a turnkey solution provider. So if we look at the major areas that we provide, it's the concentrator, the receiver, the automated cleaning system, the part level integration, steam quality, and then obviously all the installation technology as well. So this together really can help to realize the high efficiency levels and the high potential that dishes offer, and convert them into a practical reality for various applications. As you can see, dishes have been through, you know, various conditions. You know, we can withstand deep freezes, withstand sandstorms. So they're a robust technology. The other advantage is, you know, they're simple to install and commission with a small ground-mounted footprint. And, you know, they can be, and that's also why they are semi-mobile and can be transferred to a new location as needed. So looking at some of the projects we've done, some in Lahore, in Dubai at the Mohammed bin Rashid Solar Park, also in Kuwait, where we have been running systems for the national oil company there. Dishes have a lot of, you know, technical advantages, which have allowed us to, you know, win several awards, be finalists for some of them. I can see Belen is smiling because one of the awards is from CSP today in Seville. And obviously, you know, we have also been able to show our technology in several of technical papers presented in Solar Places and available online. And a picture we really like is with His Highness Sheikh Mohammed, the ruler of Dubai. You know, he likes the system a lot, so we have a very nice picture of him using the dish to actually promote their big clean energy, initiatives in Dubai. So, looking a little bit about, you know, why would you install a dish, or why would you go for solar steam in a particular location? What are the factors that need to be considered? For example, here we have a map of Pakistan, which is showing the DNI. And on the left side, we have, you know, the various fuel sources. So, you know, considering this as an example, the fuel sources are quite high, but then you also need to compare against the DNI that's available. And you can see some parts of the country have very good DNI, but then for industrial applications, you need to see if your application, your industrial base actually falls within that good DNI or within that bad DNI zone, because that obviously makes a significant difference on the cost of the solar steam and the viability of the system. So overall, I mean, why dishes for such an application over legacy CSP technologies? Well, you know, the efficiency is very high, so obviously the solar field size drops, and as the solar field size drops, the capex drops, and the O&M drops as well considerably, and also the land use, which at the end of the day is helping to, you know, bring us into a position where the project starts to make economical and financial sense for industrial applications. So that's a little bit of a quick overview on the technology and on Z Solar. Over to you, Belen.
Thank you very much. Can you go back to the, actually, I was going to ask you to go back to that slide where you had the thermal efficiency, because there's been a couple of questions about this. And there was someone here asking, how is it possible, considering reflectivity, absorptivity, what a weird word, and thermal losses? I don't know, maybe it's a bit further along, actually, where you put the 88%. So maybe you guys should take turns and explain exactly, because it seems like the issue is maybe some people are having trouble understanding the...
So I can go over this again, how this 88% comes. So the bottom left image is of the dish, and we assume 100% of the solar energy which falls on the dish. The mirrors have a reflectivity of 95.1%. That means that they're reflecting 95.1% of all the solar energy which is falling on them. And then if we look at the optical accuracy of the system, and 95.1 is being reflected back. And of this 95.1, 99.3% actually enters the receiver. It's a cavity type receiver, so 99.3% of the reflected solar energy enters into the cavity type receiver. And then the receiver itself has a conversion efficiency of 92.4% at 320 degrees Celsius. So when we add all of this up, so when we do, if I were to go in reverse, if I do 92.4 of 99.3 of 95.1, we come to the 88% efficiency. That's how it works. And this is also available in technical papers as well.
I see Sid going. Go on, do you have anything to add, or is your system similar?
Yes, absolutely. As a matter of fact, Zafir has already touched upon the key points. I think the reason this appears as such an unbelievable number is simply because it has never been this high in the industry. And I think that's part of the whole innovation that the dish technology is bringing about. The overall efficiency of the system is only a function of four things. One is the reflectivity of the mirrors. Second, the amount of energy that can actually be pumped into the receiver. Third, the internal receiver thermal conversion efficiency. And that's pretty much it. Now, in this case, as Zafir already mentioned, the numbers are incidentally actually that high because once the energy enters the receiver cavity, it has nowhere to go but actually get absorbed within the receiver in the working fluid and do all of the heat transfer within. So practically, the number is indeed about 90.3 to 94%. And overall system efficiency is about north of 85%. So it's unbelievable, but it's true.
Unbelievable, but true. There's magic. Here someone asks, piping between dishes should be much longer than between trough rows. So accordingly, the thermal losses should be much higher for dishes.
So if I can take that question, actually, I would say that the distance of the piping between dishes is completely flexible and variable. You can have very large dish parks, and as we have shown, you can actually have a very small dish park as well, much smaller than a parabolic trough park. I can also try and pull that slide up. If we look at the land requirement of a parabolic trough versus a parabolic dish for the same area, it's significantly smaller. And then also the piping that runs between in the park, the steam side piping is all insulated. So the losses are actually very, very low in that. And if we compare just quickly to parabolic trough, actually parabolic trough has very low sun concentration ratios, about 50 suns versus over 2,000 suns on average for a sun dish, which means you have very, very long evacuated tube receivers. And the hotter the working fluid gets in those, the higher the losses are because those are not insulated.
By the way, kudos on the name, Solar Invictus, absolutely love it. It's a Hollywood name.
Thanks.
Okay, the Naji has a lot of questions here. Says land requirement for 1 megawatt power plant, thermal. And also the collector area for the same capacity. Did you guys care to throw some numbers?
So we have, the figure that we have here, incidentally, on this slide is 500 tons of steam per day. And if I do a very quick calculation,
Let me
yeah,
add
sorry.
while you're at it, right? So if you're looking at if you're looking to generate 1 megawatt thermal equivalent of energy out of these dishes, you're looking at a total land requirement well within an acre. It's much less than an acre. It's roughly about 3,450 odd square meters, right? So it's, I mean, that's what the numbers look like. I mean, looking at a megawatt thermal, you're looking at a distance of barely about a land parcel, which is not even an acre in size.
Do you want to add anything, Safir? Have you managed to make the calculation?
Yeah, sorry, give me 1 second. I'm almost done.
Take your time, because there's a couple of questions here for Sid.
Yes, so I mean, pretty much in the range of what Sid's saying. So we're talking 4,500 square meters for that, for the 1 ton.
Okay.
So the 1 megawatt thermal, yeah.
Couple of questions here. Here someone asks, Pawan, who is very active, I can see he likes asking questions, based in Gujarat, as we learned. How do you see the progress of CST in India? And then there is someone else, Jacob, who's a good friend, you know, someone also in the industry that is watching very attentively, because he also has a dish company. So shout out, Jacob. He says, what is the customer cheapest alternative of heat source in India, and at what price is it? So I think these questions are more for Sid, so.
Sure. The first one, how's the market picking up in India? Well, I believe, as I probably was evident in a few slides that I had presented, that the awareness about concentrated solar thermal is gradually coming in. I believe it's an all-time high right now. And a lot of industries are coming forward to look at alternate technology solutions. And of course, the CST and a Paraboloid Dish is a good fit there. So we have seen a market that is gradually evolving, but the larger arrow is in the right direction. There's a year-on-year growth for us as a company. And we only see that this market is just going to open up more as the fuel prices are actually kind of linked to the market prices, and all the subsidy in the fuels are withdrawn, number one. The second question was more related to the cost of the existing systems in the heat. Well, it's a large spectrum, as I indicated in my last slide. It's a large spectrum which ranges from using things like natural gas and electricity for heating, which is of course a more expensive form of heating, down all the way to using very, very cheap coal and a combination of wood and biomass for heating, which is extremely cheap and a dirty form of heating. So the numbers are actually spread across all parts of the spectrum, depending whom are you talking to.
Thank you very much, Sid. I'm going to ask you, Safir, to stop sharing now so that we can see your faces up big when you talk. Excellent. Okay, so we have a couple of questions here. One is, do you have a special technique for cleaning the reflectors? So this goes to both of you. Maybe Safir, you start, and then Sid can add.
So we clean the reflectors. It's a wash and wipe method, basically. We use a little bit of water and then wipe the reflectors with our automated cleaning system. So effectively wash and wipe system.
Sid?
No different than that.
Right, so it's simple, just with a mop.
It's very simple. I mean, we do provide certain what are called automated sprinkler systems as well. So both options, being manually with a mop or automated wiper-based systems, are available.
Has anyone actually done any work on not using water at all? I mean, presumably if you are in an area with not a lot of water, you may have run into problems with that.
So if I can just take that, I mean, yes, we have looked at doing that without water. It depends on the type of dust you have, how much humidity there is, and especially how much salinity there is in the dust. So if you're in the Middle East, for example, if you put the dish to sleep at night and you avoid the salinity, then the dust does not stick, so you can actually even do a dry clean. However, if you have salinity, then the dust becomes very sticky. and then you need water to clean it. So it really depends on what sort of dust you have that you're trying to clean. Otherwise, you can do dry cleaning if not wet cleaning.
I can imagine you scratch the surface of the dish as well when you do dry cleaning.
I'd say yes and no. Again, depends on the type of dust. You can have some hard dust grains, some more soft dust grains. But the mirrors themselves are fairly resilient to being cleaned with a soft material as well, dry cleaned as well.
Interestingly, like in a conference I was a couple of weeks ago, there's been these people who are researching and they've managed to clean parabolic troughs with plasma and laser. But still, they still have to work on the system. But they say, you know, they're looking at patenting the situation because I think in the case of the desert, it's quite important as well. So hopefully, we'll see innovation going on in that area. And this is the question. Sorry, go on, Sid.
Yeah, just one point to take away. Glass is actually a back surface reflector, unlike aluminum, which is a front surface reflector. So any scratching that you do on the front surface directly impacts the reflectivity and the longevity and the durability of that reflector. However, for glass, as Zafir rightly pointed, there's not much to be worried about what you're doing on the front surface because all the magic is actually happening at the back coating of the glass. So even when you're rubbing and literally scratching that thing, there is no reflectivity to be lost unless you're actually scratching the back surface. So there's a fundamental difference between how glass mirrors get impacted while cleaning versus any other kind of films and aluminums, right? Yeah.
Well, good point. I didn't know. See, this is I've learned today. Thank you very much. So this is for the two of you. Which is like your business model like? Do you sell turnkey? Do you do ESCO models? You know, how do you serve your clients? So, Sid, do you want to start?
Sure. So we have both models, right? We have what is called a turnkey CapEx model, where we actually sell the entire system and the system actually resides on the balance sheet of the customer. Sometimes, depending on the scale of the project, depending who the off-taker is and his or her credit rating, so how solid a balance sheet the company has, we can also do what is called OpEx models, whereby we actually own and invest in the asset and we set up the entire plant. We get into what is called a long-term heat purchase agreement with the customer, and we have the proper kind of metering and performance monitoring installations on site. And the customer is essentially paying on per use basis. That could be a ton of steam, it could be kiloliters of hot water, it could be tons of sludge, as I mentioned. So we do both, depending the scale of the project and who the end customer is.
Zafir, what about you?
Yeah, so very similar to what Siddharth has already mentioned, you know, we do the CapEx model and also the ESCO model. I mean, it really depends what the preference of the client is and on you know, how solid and how reliable a client they are, if we can do a long-term steam purchase agreement with them or not.
So what you're seeing more, do people go for the CapEx side of things or the ESCO side of things?
I would say, I mean, it really depends from client to client. Obviously, if it's a CapEx model, they will save more money. So I think I would say it's probably split fairly evenly right now, but it's more dependent on their individual situation.
Yeah.
Okay.
I believe it's an industry that is, at least in India, gradually moving towards an OpEx model. And the reason I say that is most industrial customers that adopt this recognize that this is not a core asset for them. This is not a part of their core business. They might be in the business of dairy or automobiles and whatever have you. They quickly recognize this is a non-core asset and they want to treat this like a utility. So the idea of a third party coming in, installing the system like a black box and simply delivering the heat to the end customer is something that is quickly picking up. And I'm glad that we are kind of leading that change in India.
So CSH as a service then, guys. This
Yes.
is what we're seeing more of. It's not, I mean, it's completely expected, I suppose. I think most industries are moving in that direction. So it's no big surprise. Just, you know, to finalize, I suppose there is no minimum really for your plants. It could be just one dish would be enough? Or do you have a minimum that, you know, that needs to be larger than that?
And I would say that's the beauty about dish concentrators, and I'm sure Zafir would probably not disagree, that the modularity of the system actually lends itself to doing a project that could be a very small project of 1, 2, 3, 4 dishes, and of course to doing a very large solar field as well, because the modularity allows you to scale up the economics as well. So yes, we do projects across scales.
Okay, and some advice. Pawan here, who had a lot to say, was saying, you know, we're trying to get a CST project, but nothing's turning up. You know, they have a parabolic trough, so it's a different system. So the question, this is something that I asked you before when we were offline, is how hard is it to sort of find those leads, those customers? How difficult is it to convince them? I have to say, I've been working for a little while with CSH technologists, and they find this is the hardest part of the job, to, you know, do the lead generation. So I suppose I would appreciate if you could give some maybe some advice to Pawan, and this will be the last question, and then we'll just have to say goodbye. So Sid, do you want to start, and then maybe Safir can take it from there?
Sure. Well, in a nutshell, it's like eating glass, right? it's very hard. It's hard in the sense that, especially in the onset of PV, and I only use PV because while it does not generate heat, but the investment dollars compete between PV and solar thermal, right? So from that perspective, it's interesting the time it takes to kind of have an initial lead generation and convince the customer, understand the application, propose an integration that the customer's engineering team feels very comfortable with, and then of course then close the project and actually go on to execution. That being said, we have seen a trend where awareness is being very, very high. I believe it's an all-time high right now. And that is making things easier. We are at least looking at doing projects outside of India, and we have some experience doing projects in Southeast Asia and China. And that is through representatives, that is through dealers, that is through consultants, other OEMs who are actually closer to the customer that help in lead generation. And of course, then our project and sales team are in there to support them. So it's been good, and I think it's only going to get better from here on.
I actually remember when you were starting out, and like obviously now you have a big portfolio of projects, but this wasn't the case a few years ago, and you still kind of managed to get there.
Sure. Well, it's taken some time, but the brave ones will survive.
Safir, anything to add?
Yeah, I mean, I think the most important points, perseverance is very, very important, and being, you know, not giving up. But apart from that, I mean, you know, finding the right markets where the solar conditions are right, so that actually, you know, you can provide a good economical solution, financially viable solution. And then, of course, as Sid said, you know, having the right representation in local markets, you know. If you want to work outside your home territory, you cannot just expect to fly somewhere and to do a deal and come back. You need to be on the ground, and you need to follow up and pursue clients. Otherwise, you will not have any success.
See, it happens to me too. I forget I am muted. Thank you very much, guys. It has been great talking to you. I see that we have a few friends also listening at the moment, people who are in the industry as well, or related, or people who, you know, I've been working with for many years. So thank you very much for attending. Thank you very much for speaking. Thank you, Safir. Thank you, Sid. And I'm looking forward to seeing you guys all again in the next session. You know, we have sessions about all kinds of topics. We're doing a lot of stuff on CSH. So appreciate your continued support for this program, and hopefully see you in the next one. Thank you very much.
Ciao.
Thank you. Bye.
Bye.
Pleasure.